All right, according to my watch, it's basically noon Pacific, 3 Eastern, and probably 9 o'clock where you are, Christian.
That's right.
So it's my pleasure to start the final session of this conference and to invite Christian Vergu from Niels Bohr to Institute to talk about Calabi-Yau's for scattering amplitudes from twistor geometry. Christian, please go ahead.
Thank you, Lance. Thanks to the organizers, and thank all of you for tuning in or zooming in or whatever the appropriate verb is. So this talk is a continuation of the talk that Andrew gave just before, and it's in collaboration with a bright PhD student here at Niels Bohr Institute, Matthias Volk, and it builds on previous work that Andrew reviewed. So the main idea of this talk is, what if we took the analysis that Andrew presented of a certain subset of integrals that he talked about, and instead of doing the analysis in terms of Feynman parameters, just do it in twistor space, see what happens. So that's the question I will try to answer.
Christian, could you speak up just a little bit more?
Yeah, so so the context, what's the context? The context is, just to make it self-contained, so we've seen that iterated integrals have appeared a lot in the calculations that people have managed to carry out, and of course they're very interesting numbers theoretically, and by now there's technology to work with them, and even if we're not at the level where everything can be completely automated due to algebraic complexity, it's a relatively well understood class. So so that's the situation as far as this class of integrals is concerned. However, if you start looking at higher loops, you will notice that pretty soon you run into various obstructions, right? So as far as we know, this new class of things is not going to be of iterated type, and moreover, they're very interesting because they are of Calabi-Yau type. So inside of this geometry, as I will explain, inside of these integrals, you can find Calabi-Yau geometries, and this is very unexpected, I believe, and it's very interesting. And it just indicates that we really need to go beyond the just this class of iterated integrals that we know and love. So I will try to provide some elements of answers, not completely answer these questions, but just give you some indications of how we might eventually answer them. So the first one is when do these Calabi-Yau varieties appear, right? So if you start with an integral, you would like to know beforehand, when do you expect to have a Calabi-Yau inside that? And the second question is, why are they Calabi-Yau, right? And then the third question is, given the knowledge that we have that they're Calabi-Yau, what can we say about their topology? And the fourth question that I will address, which in fact has not been really looked at so far in detail, as far as I'm aware, is the question of supersymmetrization, right? So if you do this analysis in n=4 theory, you find these geometries, and somehow you have to reconcile this geometry. You have to put it to make it so that supersymmetry acts in a natural way. So how does that work? That's the question number 4. Right. So just for definiteness, I will focus on a subclass. So these were called train track integrals, where they were studied by these authors here, and so it's a string of boxes with some extra legs sticking out here, and these legs here you can make massless or massive. I'll mostly keep them massive, just to be in a generic case, but you can degenerate to the case where they're massless. And on top of this, I superpose the dual diagram. So I'll work with both of them. So for the dual diagram, you have a dual variable inside every loop and a dual variable outside. Now, there are two ways to check. As far as we know at this point, if you have an integral and you want to see if there's a Calabi-Yau geometry inside, there's two ways you can try to check this. And one is you can try to apply this procedure of direct integration that Andrew also mentioned. And so you do that and you keep integrating, and you're going to generate polylogs, and then you're going to have some differential form here. And at some point, you will not be able to do integrals to obtain polylogs anymore, right? So the example that, the simplest example of this type of behavior is when you have some genus 1 curve, right? So it can have an equation of this type. Y squared is some degree 4 polynomial, say, and then omega is going to be some differential form of this type. Now, this is the hard way. You do integrations. And the easy way is you compute residues. So you start with some integral, and you compute residues around poles. And you do this until it's not possible anymore, right? So during this procedure, you can generate Jacobians, and you can also take residues of Jacobians, and so on. And you do this until there's no more residues, right? So here there's two options. Either you obtain a constant, right? So some zero form, and then this integral is called pure. And in cases where it's pure, all the examples that we know so far, it's possible to integrate it in terms of generalized polylogarithms. But it may also happen that you don't end up with a zero form. So at the end of the day, you keep taking residues, and you're left with some differential form, which is non-trivial. And that's mostly the situation I will study. I will not do a direct integration, but I will just take residues. So to do residues, it's very convenient to use momentum twisters. And momentum twisters are a way they were introduced by Andrew Hodges with the purpose of making dual conformal symmetry manifest, right? So the integrals that I'm studying here all have a property of dual conformal symmetry. That's why I'm using also the dual space description. And all you need to know about momentum twisters is all that I'll use in the following is in this table here, right? So to every point in dual space, I can associate a line in momentum twister space, which is just a copy of the three-dimensional projective space. And if I have two null separated points, x and y, to each one of these points corresponds a line. So I have the line Lx and the line Ly. And the constraint that they're null separated is just the constraint that the lines intersect in P3. So this is very useful because now I can encode the on-shell condition and the propagators in a geometric form in terms of intersections of lines. So let's start with the train track integrals that I told you about, and let's look at the left side. So here I have one internal dual point and three external dual points. And it's a geometric fact that so to each of these three external dual points, I can associate one line. And since I assume that all of these masses here are generic, so not all of these external legs are generic, not massless, the three lines are skew, so they don't intersect. And then there's a geometric fact that three skew lines in P3, there's a unique quadric that contains all of them. And the quadric has the property that it has two families of rulings. So there's two families of lines. This is the red family are here, and then there's the green family of lines, and you can see that I can sort of move this green line around. And so this green line, there's a whole family of green lines which intersects all three of the red lines. So in other words, it's null separated from all of them. And this is a one-dimensional space, right? So you can imagine dragging this line along the quadric, and that's going to give you all the solutions of these three constraints here. So if I add the second part, right? So this is, I looked at the left end, then you put the right end. The right end is the same thing, right? It's another copy of this. It's another quadric. And the intersection will be, every point in the intersection gives me two lines. One line that intersects the three lines in the left quadric, and another line that intersects the three lines in the right quadric. So this solves all the constraints. And so what we have now is that the space of the leading singularity locus of the two-loop train track integral is just an intersection of two quadrics in P3. And this is the second geometric fact that I will need, is that the intersection of two quadrics in P3 is just some genus 1 curve, right? So here I try to present a drawing of this. Of course, this is in a real projective space, so it looks like the curve is disconnected, but in reality, once you study this over the complex numbers, it's going to be a nice smooth connected curve, complex curve. So this fact was known. The fact that for this two-loop integral was called the elliptic double box, and it was known already that this is a genus 1 curve. But here we just found it from twistor space analysis. Right. So we found the leading singularity locus, which is just this is what I told you. It's an intersection between the left quadric and the right quadric. Right. So for every point on this intersection, there's a green line in the left and in the right quadric that intersects all of the external the lines corresponding to external points. And even more, I can now obtain the holomorphic 1 form on this curve, right? So that's another important ingredient. And the holomorphic 1 form can be found by taking two Poincaré residues. So I can start with this PGL4 invariant form on P3. I divide that by the product of QL and Q right, and I take a residue in QL and Q right. So I take two residues. I start with a 3 form here. I take two residues and I end up with a 1 form. And so here, another thing I should mention is that this 3 form on P3 has weight 4, right? So if I rescale the coordinates by some non-vanishing constant, I get something to 4th power. And in the denominator, I also get something to 4th power. So this is it's a homogeneous ratio, right? So this makes sense in projective space. Right. So I obtained the geometric description of this genus 1 curve as an intersection, and I obtained the holomorphic 1 form on it. And so now the question is, how do I compare genus 1 curves, right? So I would like to compare, for example, the construction that was done in other ways, right? If you start doing this integral by Feynman parametrization, for example, you will obtain the result in a very different way. So the way to do that is to compare the J invariants. And actually the J invariant is some quantity that I would like to advocate to parameterize these genus 1 curves, because in fact it will turn out that it will be rational in the external kinematics. So the way you find it is I had this left and right quadric, but in fact the curve C can be obtained as an intersection not only of QL and Q right, but as intersection of any two linear combinations of QL and Q right? So really I should consider a whole family of linear combinations of QL and Q right, and this is called a pencil. And this quadratic, this quadric here becomes singular at 4 points in P1. So there's 4 values of mu0 and mu1 for which this quadratic form is singular. And then using these 4 points, I can build a cross ratio lambda, and then the J invariant is just this expression. And in fact, we compared the J invariant for this obtained in this way, the J invariant obtained by doing the integrals and in Feynman parametrization, and they perfectly agree. So this is a good way to characterize your genus 1 curve. Now the 3-loop case was analyzed by these authors, right? So the integral looks like that, and the dual diagram looks like that. And this can also be done in momentum twister space. And the construction is a bit more involved, but just from the geometric fact I told you that two lights, so all of these segments here correspond to light-like separated intervals. And you can just impose the conditions that are written here, right? So I have to find a line LB that intersects L4 and L8. And then I have to find a line LA that intersects 1, 2, and 3, and a line LC that intersects 5, 6, and 7. And so this is the picture, right? So I have these 2 lines that correspond to the top and the bottom. And then I have the line, this gray line, if you can see it, that's transversal to both of them, which is corresponds to this point B. And then I have this line intersects each one of the quadrics in 2 points each. And then from the points here, I can draw a line that intersects the 3 external points in the left and the 3 external points in the right. So from this construction, I can see that I can realize the leading singularity locus of this diagram as a branched cover over P1 times P1, right? So what does this mean? It means that for every choice of a point on this line and choice of point on this line, there's two solutions for the loop momentum in the left box, and two solutions for the loop momentum in the right box. So this is why it's branched, because there's several copies. Now there are special points where this line becomes tangent to the quadric, and in that case there's no branching for that particular loop. There may be a branching for the other loop. Right, so this is what I told you. There's so for every choice of points P1 and P2, there's a line. It intersects QL in 2 points, intersects QR in 2 points, and then there's all the solutions that you get by intersection with the quadrics. And this is kind of an analog of what you have. This is probably much more familiar. That there's a situation where you can have you can realize an elliptic or a genus 1 curve as a double branched cover over 4 points in P1. Okay, so I'm running out of time fast. So this is so one thing you can do now is you can try to compute the Euler characteristic of this variety. And the way you do it is by using all these properties of the Euler characteristic. So we will cut and paste all these copies. So there's 4 copies in P1 times P1 minus the union of the two curves C, where you get a tangent to either one. So there's a CL and a C right, where you get a tangent at the left and the right quadric. And there are 2 copies over the union minus the intersection. There's 1 copy for the points where you have just the intersection of the 2 curves. And then I use these properties of the Euler characteristic. And in particular, the CL and C right are themselves some kind of tori. Again, perhaps in a less familiar realization as bi-quadratic equations in P1 times P1. And then I finally use this inclusion-exclusion property. And then you put everything together and you find 24, right? So 24 is the expected answer. You can, if you look at the Hodge diamond of K3, it has all these entries, and then you add them all up, which is what you need to do for the Euler characteristic. You get 24. So one other thing we can do here, since all the K3s have the same Hodge diamond, you obviously cannot distinguish between them just using this information. So one other thing we can do is we can see that this is a space of K3s that has a moduli space of dimension 11. So out of all the kinematic degrees of freedom that you have for 3 loops, only 11 of them actually change the shape of this surface. And this tells us, there's a theorem that tells you that the generic Picard rank and the dimension of the moduli space have to sum to 20. Right, so the threefold, we looked at the threefold. The threefold can be realized inside of a toric variety. I'm not going to explain what this means, and it's a complete intersection Calabi-Yau. So this is a special class of Calabi-Yaus, which is a pretty large, can give you a pretty large set of Calabi-Yaus, and you have some embedding variety, and then you have some equations. And we computed these Hodge numbers. We actually used a computer program by Kreutzer et al. That uses some combinatorial results of Batyrov and Borisov to, so it just amounts to counting points in various simplices. Now, one thing I should say here is that as you go higher in loop order, these complete intersections become very high codimension. And of course, that makes them hard to analyze. Right, so I promised you I will tell you a little bit why these are Calabi-Yau. So obviously, I'm not going to give you a proof. I will content myself with some plausibility arguments. So momentum twistor space, what it does for us is that it provides some compact, complex scalar embedding space. And these are all required for Calabi-Yau. And also we have some a nice nowhere vanishing differential form to start with, right? So in the case of the genus 1 curve, we had this PGL4 invariant form. And then what we do is we take Poincare residues, right? Just like I showed you for the genus 1 curve. And you take residues until you cannot take residues anymore, right? So at that point, you have a holomorphic form, right? So well, one way you can define Calabi-Yaus is just it just lists all these properties. Is compact, complex, scalar with a nowhere vanishing holomorphic top form, right? So they all seem to be part of this. Now I should make some qualifying comments here. Is that of course for some values of the kinematics there may be singularities, right? And then at those special points, it becomes possible to take further residues, but generically this will not happen. And the other caveat is that, of course, there may be several holomorphic top forms. And this perhaps seems hard to believe, but it could happen. So obviously we didn't exclude this possibility.
Hey, Christian, just a quick comment that we're technically into the question period now.
Yeah,
so
sorry. So maybe just I'm going to skip over this quickly. So the point of the supersymmetrization is that all the construction that I discussed before, they used lines. Everything was about lines, and these lines can be obviously supersymmetrized. And so that's how supersymmetry works. That I think that's all I'm gonna say about this. And I'll end with some open questions. So there's this mirror symmetry story a la Bloch, Kerr, and Van Hove. How is that going to work here? Topology at higher loops, non-planar integrals. So non-planar integrals, of course, applying momentum twister to those is a bit trickier, maybe still possible, I'm not sure. And of course, the hardest question is how do you explicitly compute these integrals? Okay, thank you.
Okay, it's time for a couple questions. I see a hand up from Claude. Claude, could you unmute yourself and ask your question, please?
Yeah, so thanks, Christian. So I have actually two questions. The first is, so you refer to the J invariant as a way to kind of identify the curve. And then, as I understood, you're also saying, okay, now I have maybe ways to identify or characterize my K3, right? But we know already that for the sunrise, there is no such thing as this sunrise of the curves, depending on how you do the calculation in different J invariants. There are actually curves that you get depending on how you do the calculation from cuts or from final parameters are exogenous, not isomorphic.
Well, so I believe that, so I looked at this a little bit, and I don't fully understand what's happening there, but something is going wrong, clearly.
What do you mean
Uh,
it's going wrong? I mean,
uh,
you look at
Something is wrong. I
calculation.
mean, uh, I've looked at this, and there's some strange things happening, and well, maybe we can discuss this later. I'm just skeptical of the fact that you see what this would seem to indicate is that somehow. Depending on how you do the calculation, you can get all kinds of different J invariants. And I'm skeptical that this should happen. And one of the reasons I'm skeptical about that is that, as far as I know, at least, there's no notion of isogeny that works for K3s, right? So for the elliptic case, you can say, well, they're not the same, but there's this other thing that you can use instead. Now, for K3, they're either the same or there's no. This is not a group. The K3s. It's a very different situation, right? So, the genus 1 case is a very special case where you can do more things, and there's certainly something funny happening there, and we can discuss it later. My opinion right now is that I would hope that something is wrong, because otherwise it's very hard to understand how you can okay, at the very least, there's a construction which is kind of analogous to what I described, and that gives you a well-defined answer. And that answer is the same as the answer that you get from the Feynman parametrization. If you start doing Bykov or other things, you indeed seem to get something else, but I wonder if that's completely legitimate or not. That's
maybe we can take the rest of this question offline. I see our Nima has a question.
Yeah, just quickly, can you comment on on another intuition that is often used to say that things should eventually get arbitrarily bad, which is exactly that, as you said, we get singularities, leading singularities, singular loci, when all these quadrics in the propagators intersect each other. And while when we intersect hyperplanes, we get other hyperplanes, when we intersect quadrics, I think we've known since the 1980s, we can realize an arbitrary algebraic variety by intersecting quadrics. So that was always, I thought, some intuition why things are bound to get arbitrarily bad. As far as the yeah. Anyway, that's some other intuition. Do you know how that intuition meshes with the way you're thinking about things? I mean, it's true if we have planar diagrams, maybe that we can't let the quadrics intersect arbitrarily, but that seems like a very minor restriction.
Yeah. So I mean, indeed, things. Okay. So in the planar case, I'm moderately optimistic. I mean, I think every one of these lines has a certain number of neighbors, and all of these equations are in fact linear in every single one of the variables. So those are not so bad. The ones that are bad are.
So you think planarity might restrict the kind of intersections of quadrics that we end up getting?
Yeah, the ones that are bad are the ones like this, right? So if you have something like this loop here, well, let me show you. This loop here is not so bad because it's got linear things, right? So it's all, but this one has quadratic things. So yeah, in other words, if you look at this story here, these are degrees, this one has degree 2 and 2, degree 2 and 2, the equations that carve out a variety inside of this space. But this one has 1, 1, 1, 1, right? So yeah, it seems like there's going to be a bunch of these type of things which are perhaps not so bad. Yeah, it's kind of a vague
Okay,
intuition.
thank you.
Okay, I don't see any more questions. So let's thank Christian again. I'm not going to unmute all this time, so we can use the other method. And yeah, thank you again, Christian. And